In modern web application development, building systems that are scalable, maintainable, testable, and easy to extend is extremely important. Traditional software designs often suffer from tight coupling, where components directly depend on concrete implementations. This approach makes applications difficult to modify, test, or scale. To solve these problems, modern frameworks such as ASP.NET Core strongly rely on two powerful architectural concepts: middleware pipeline and dependency injection, DI. Together, they form the backbone of how HTTP requests are processed and how services are managed within the application. When a client such as a browser, mobile app, or external system sends an HTTP request, the request does not directly reach the controller or business logic. Instead, it passes through a structured sequence of processing units known as the middleware pipeline. Middleware components act like checkpoints. Each middleware can examine the request, perform some operation, and then either pass the request to the next component or stop the pipeline and return a response immediately. This layered processing approach ensures clean separation of responsibilities and flexible request handling. The middleware pipeline works in a sequential manner. The request enters from the left side and flows forward through each middleware. After reaching the endpoint and generating a response, the response travels backward through the same middleware components in reverse order. This bidirectional behavior allows middleware to modify both incoming requests and outgoing responses. For example, a logging middleware can log both request details and response execution time, making it extremely useful for monitoring and diagnostics. The first middleware typically present in most applications is the logger middleware. Logging is essential for understanding application behavior, detecting errors, tracking performance, and auditing system activity. When a request arrives, the logger middleware captures information such as request path, HTTP method, headers, timestamps, and later the response status code. Instead of creating logger objects manually, ASP.NET Core provides logging services through dependency injection. The middleware simply requests an iLogger interface, and the DI container automatically supplies the correct implementation. This design removes hard dependencies and ensures consistency across the entire application. After logging, the request usually flows into the authentication middleware. Authentication is responsible for verifying who the user is. This middleware checks credentials such as JWT tokens, cookies, API keys, or OAuth tokens. The middleware itself does not know how users are stored or validated.
It relie en abstraction trois interfaces like authentication service.
The actual implementation, whether it connects to a database, identity server, or external provider, is injected by the DI container. This separation allows developers to change authentication mechanisms without rewriting middleware logic. Following authentication comes the authorization process, which determines whether an authenticated user has permission to access a resource. Although sometimes combined conceptually, authentication verifies identity while authorization verifies access rights. Authorization middleware evaluates policies, roles, and claims before allowing execution to continue. Because authorization logic depends on policy providers and rule engines, dependency injection plays a major role here as well, enabling flexible security designs. Next in the pipeline is the routing middleware. Routing is responsible for mapping the incoming HTTP request to the correct endpoint. It analyzes the request URL, HTTP method, route parameters, and metadata to determine which controller action or minimal API method should handle the request. Routing middleware uses centralized route definitions registered at application startup. These routing services are injected from the DI container, allowing the routing system to remain configurable and extendable. Once routing is complete, the request enters the endpoint middleware, which executes the matched endpoint. At this stage, the real business logic begins. Controllers or endpoint handlers perform operations such as reading data, validating input, processing rules, and generating output. Endpoint execution often requires access to databases, external APIs, caching systems, and internal services. All these dependencies are resolved using dependency injection, keeping the endpoint logic clean and focused only on business behavior. One of the most important services used at this stage is the database context, commonly represented by DB context in Entity Framework Core. Database contexts are registered as scoped services, meaning one instance is created per HTTP request. This ensures transactional consistency and avoids concurrency issues. Each request gets its own database instance, and once the response is completed, the instance is disposed automatically by the framework. After endpoint execution, the response may pass through custom logic middleware. This middleware can perform tasks such as global exception handling, response formatting, compression, caching, or performance tracking. Custom middleware is entirely developer-defined and plays a major role in cross-cutting concerns. These components also benefit greatly from dependency injection because they can use services like email senders, notification systems, or monitoring tools without tightly coupling the code. At the foundation of this entire architecture lies the dependency injection container, which in ASP.NET Core is built-in and highly optimized. The DI container is responsible for creating objects, resolving dependencies, managing lifetimes, and disposing services when they are no longer needed. Developers simply define which services are available and how long they should live, and the framework handles everything else automatically. The DI container supports 3 primary service lifetimes.
The first is Singleton lifetime.
A Singleton service is created once when the application starts and shared across all requests. Services such as configuration providers, application settings, and shared caches are ideal candidates for Singleton lifetime. However, Singleton services must be thread-safe because they are accessed simultaneously by multiple requests. The second lifetime is Scoped lifetime. Scoped services are created once per HTTP request. Every component within the same request receives the same instance. This lifetime is especially important for database-related services, transaction managers, and user-specific data handlers. Scoped services provide isolation between requests while maintaining consistency within a single request.
The third lifetime is Transient lifetime.
Transient services are created every time they are requested. These services are short-lived and stateless. Examples include email services, SMS services, and helper utilities. While transient services provide maximum isolation, excessive use can impact performance if the objects are heavy. An important concept shown in the diagram is the per-request scope boundary. This boundary defines where scoped services exist. When an HTTP request begins, the DI container creates a scope. All scoped services are resolved within that scope. When the request completes and the response is returned, the scope is destroyed and all scoped services are disposed. This automatic lifecycle management greatly reduces memory leaks and resource misuse. One of the greatest advantages of dependency injection in middleware is loose coupling. Middleware depends on abstractions rather than concrete implementations. This allows developers to change implementations without touching middleware code. For example, an email service can be replaced with a different provider simply by updating service registration. Another major advantage is testability. Middleware and endpoints can be tested independently by injecting mock or fake services. Developers can simulate databases, authentication systems, and external APIs without relying on real infrastructure. This makes unit testing faster, safer, and more reliable. Maintainability is also significantly improved. Since service registrations are centralized in one location, usually in program's application structure becomes clean and organized. Developers can understand the system by examining service registrations rather than tracing object creation across the codebase. Dependency injection also enhances scalability. Proper lifetime management ensures efficient memory usage and controlled object creation. Applications can scale horizontally across servers without worrying about shared state corruption. DI also supports cloud-native architectures, where stateless services and short-lived objects are preferred. From a real-world perspective, middleware combined with dependency injection is similar to an assembly line in a factory. Each station performs a specific job, and shared tools are provided when needed. The workers do not build tools themselves, they simply request them. This results in faster production, fewer errors, and easier upgrades. In enterprise-level applications, this architecture becomes even more powerful. Large systems may include dozens of middleware components handling security, rate limiting, telemetry, caching, compression, localization, and auditing. Dependency injection ensures that all these components work together without becoming tightly bound. Another important benefit is separation of concerns. Middleware focuses on request processing, services focus on business logic, and the DI container manages object creation. Each part has a single responsibility, which aligns perfectly with solid design principles. The use of interfaces also allows easy integration of third-party libraries. Logging frameworks, monitoring tools, payment gateways, and cloud services can be plugged into the application simply by registering them in the DI container. This makes ASP.NET Core highly extensible and adaptable to changing business needs. Performance is also improved because the framework optimizes object creation and reuse based on lifetime configuration. Singleton services reduce overhead, scoped services balance safety and efficiency, and transient services provide isolation when needed. This fine-grained control allows developers to tune application behavior precisely. In large distributed systems, middleware often plays a role in implementing cross-cutting architectural patterns such as circuit breakers, retries, fallback strategies, and rate limiting. Dependency injection ensures these patterns remain configurable and reusable across different applications. Another powerful advantage is consistency. Every request follows the same pipeline, ensuring uniform behavior. Logging, security, and error handling are applied consistently regardless of which endpoint is accessed. This predictability improves system reliability and debugging efficiency. From a learning and interview perspective, understanding middleware with dependency injection demonstrates strong backend architectural knowledge. It shows that the developer understands not only syntax, but also design principles, runtime behavior, and enterprise patterns. In conclusion, the integration of middleware pipeline and dependency injection is one of the most powerful features of ASP.NET Core. It provides clean architecture, loose coupling, effective lifecycle management, strong testability, and excellent scalability. Every HTTP request flows through a well-defined pipeline, receives required services from the DI container, executes business logic safely, and returns a response in a controlled manner. Mastering this concept is essential for anyone aiming to become a professional backend or full-stack developer.